Okay, I'm going to start using this text here, and this is an absolutely wonderful book, and if you can get a copy of it, please do. It's well worth having. And the first part is a review for us because we've covered some of this material, but I think it's worthwhile to go through his discussions. So chapter 4 is probability distributions. So suppose a couple plan to have 3 children, and they're interested in the number of girls they might have. This is an example of a random variable and is customarily denoted by a capital letter, capital X in this case, the number of girls. The possible values, of course, are 0, 1, 2, or 3 girls. However, they are not equally likely. To find what the probabilities are, we must examine the original sample space. So, what do we mean by the original sample space? So, if we're planning to have 3 children, we think about the sequence of boys and girls. So you could have boy, 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 you could have boy, boy, girl, and so on. That's the original sample space. And in chapter 3 said, already calculated in figure 3.3. And it's repeated in 4.1. So let's take a look at that. So here it is. So this is the sample space, and these are the probabilities for each of them. Now he's using, by the way, I forget, I think the probability for a girl is higher. No, I don't remember. Probability for, well, let's see. Probability for a girl is lower than the probability for a boy. So the probability for 3 boys is higher than the probability for 3 girls. So he's not using 50-50. And his numbers are actually more accurate. It's not actually 50-50. It's the probability for a boy is higher rather, than the probability of a girl in reality, in human beings. Okay? So, anyway, so with, I think he uses this one, boy is 52% and girl is 48%. So using those numbers, you will come up with the probability of girl, girl, girl. Remember, each time is independent, right? Each child is independent of the previous one. So this would be the probability of girl and girl and girl, or I should say the probability of girl in the first child and girl in the second child and girl in the third child. Those are 3 different events. They're each independent. So we can, since they're independent, if you remember the rule about probability of independent events, you should remember that you can split it up into the probability of the first event times the probability of the second event times the probability of the third event. So that would be, I think I said it was 48% times 48% times 48%. That supposedly, I guess, will give you 11%. Whereas this one would be 52% times 52% times 52%, and that supposedly would give you this. Whereas this one would be 52 times 52 times 48, and this would be 52 times 48 times 52, which of course would be the same probability as this, so you get 0.13, 0.13, and this one also you get 0.13. Okay, so that's the idea. Now, the random variable, though, is the number of girls. So X stands for the number of girls. So X can be 0, 1, 2, or 3. So 0 means all boys. 0 girls means all boys. So that's this one gets mapped to 0. This one, and this one all have how many girls? They all have 1 girl. So these 3 get mapped to 1. And these 3 here get mapped to 2. And this one gets mapped to 3. And so what's the probability of 0 girls? X equals 0 is 0.14. So he puts 0.14 here. But what's the probability of 1 girl? That's this number plus this number plus this number, which is 0.39. So he puts 0.39 here, and so on. He says this is kind of like a new, smaller sample space. So the sample space is, in a sense, 0, 1, 2, 3 only, and these are the probabilities associated with each of those possibilities. Okay. So he says here that thus, for example, the event of exactly one girl, that is x equals 1, consists of the three outcomes, each having probability 1.13, hence its probability is this. So that was this calculation here. 0.13 plus 0.13 plus 0.13 gives you 0.39. Similarly, the probabilities of the other events are computed. Thus, we get the probability distribution of x shown at the right. So this is called the probability distribution of this random variable. He says in figure 4.1, the original sample space, which had 8 possibilities here, has been reduced to a new, more convenient numerical sample space on the right. So this was the sample space, but now we've reduced it in a sense to another sample space, which is actually a numeric sample space. This is not really a numeric sample space, and it's also smaller, as he says. Reduced. The original sample space was introduced to enable us to calculate the probability distribution P of x for the new sample space. Having served its purpose, the old unwieldy space is then forgotten. The existing questions can be answered very easily in the new space. For example, referring to figure 4.1, what is the probability of fewer than 2 girls? That is, what is the probability of fewer than 2 girls is this, right? The probability that x is less than 2, because x is the number of girls. So what is that? Probability that x is less than 2 is probability that x equals 0 or 1. And what is that? 0.4 times 0.3, I'm sorry, 0.14 times 0.39. And why do we add them? Because they're mutually exclusive. If you think about it, that means we can add them. Okay, so it's the probability of 0 plus the probability of 1. This plus this is 0.53. Okay. Now he says a more rigorous treatment, more mathematical treatment, I guess. Although the intuitive definition of a random variable in 4-2 is usually enough, in this brief optional section we give a more careful definition. As figure 4.1 shows, the random variable x associates each outcome e with a number x. Let's just check that. A more rigorous treatment. Okay, although the intuitive definition of a random variable in 4.2 is usually good enough, in this brief optional section we give a more careful definition. In figure 4.1 shows, the random variable x associates each outcome e with a number x. So what is he talking about? He's talking about this picture, and he's using little e, just little e here. He's using this little e here to mean the different sample points. There are each e, like this would be little e1, this would be little e2. We used to we didn't call it e1, e2, and e3. We just referred to them as the sample points. They are each of the elements in the sample space. So we called them the sample points. This whole thing is called the sample space. He calls this one e1, this one e2, e3, little e1, e2, e3, and so on. Okay, so he says, as figure 4.1 shows, the random variable x associates each outcome e with a number small x. So this gets associated with 0. No, I'm sorry. Yeah, this gets associated with 1. This also gets associated with 1. This also gets associated with 1. So each one of these gets associated with a number small x. This relationship is shown by the blue arrows. The blue arrows. And is a kind of function, right? This is a function, right? We're going from this set of elements to this set of elements. So that's a function. In fact, a random variable is mathematically defined just this way, as a numerical valued function. Numerical valued means that this set is numbers, are numbers. Okay, so that means it's numerically valued because we take this and map it to a number. We take this and map it to this number. We take this one and map it to the same number. So the value of the function, the outcome of the output of the function are numbers. So we call it a numerically valued function, defined over, and the input, or the domain of the function, is the sample space. So the sample space is the domain, and the codomain is this set here. Okay. This definition stresses the random variable's relation to the original sample space. Thus, for example, the random variable y equal to the number of boys is clearly a different function, clearly a different random variable than x equals the number of girls. Yet if boys and girls were equally likely on each birth, which he says they're not, x and y would have the same probability distribution. Right? So if boys and girls were equally likely, then if this was the probability distribution for, well, if we had a probability distribution for equally likely case of all of boys, we'd get a certain set of numbers here, but it would be the same thing for girls if boys and girls were equally likely. And anyone who used the loose definition 4-2 might be deceived into thinking that they were the same random variable. In conclusion, there is more to a random variable than its probability distribution. Actually, I'm not sure what he means by that, but anyway, let's continue. These ideas will be easier to keep in mind if we use appropriate notation. A capital letter such as x represents a random variable, so we'll use capital letters to represent random variables, while small letters represent a specific value that random variable may take. So we saw that already in the picture, right? Capital X is the random variable, small x are the values that random variable can take. So the random variable is like the whole picture, kind of a weird thing to say, but the random variable is like this whole picture, but the values that the random variable can take are just these numbers here. Because I say the random variable is the whole picture because the random variable is a function, and this picture is a function. Okay, so if these values are 0, 1, 2, ... then they form the new small sample space. Their probabilities are denoted by p of 0, p of 1, p of 2, and so on, or p of x in general. This notation, like any other, may be regarded simply as an abbreviation for convenience. Thus, for example, to denote the probability of one girl, we could write it this way, and I think I said somewhere, at least maybe not in my videos, but in some discussion, that I would actually put quotations here and here. Okay, so that means, just to emphasize the fact that what's going on in here is an event. So if I put a quotation mark here and quotation mark here, then I would be saying the name of the event is x equals 1, but it's still an event. Okay, so I don't know if you like that or not, but anyway, this is actually an event inside here because we ask for probabilities of events, and then he says we can abbreviate this like this. So I actually would use quotation marks here, and then I would consider this as an abbreviation of that without the quotation marks, and then this would be even a further abbreviation. Okay, anyway, enough of that. So p of 1 just means the probability that x equals 1. Okay, so here we have a picture of the distribution. So the random variable can only be 0, 1, 2, or 3, if we're talking about the number of girls. in a 3-child family. And the number, if the probability of 0 is a certain thing, it's, well, I think we said it was 0.13. The probability of 1 girl was up here. The probability of 2 girls was here, and the probability of 3 girls is here. Okay, so the probability that x is less than 2 means the probability that x is 1 or 0 means this one plus this one, which is this plus this, which is 0.53. Okay, next he says, finally we emphasize the difference between discrete and continuous variables. So discrete and continuous random variables. A random variable is called discrete if it has just a finite or countably infinite set of values. For example, when x equals the number of heads in 3 tosses of a coin, then its values are only 0, 1, 2, 3, which is certainly a finite set. Or even if x equals the number of tosses required to get the first head. Now, if you toss a coin and you keep tossing it until you get a head, and then record how many times you had to toss it to get heads, you might have to toss it just one time. The first toss you might get heads, so you only had to toss it once. But you might have to toss it twice in order to get your first head. Or you might have to toss it 3 times, or 4 times, or 5 times. In fact, it's 1, 2, 3, 4, 5, dot, dot, dot. This is still called countably infinite. It's clearly infinite, but this type of infinity is, in mathematics, is called countably infinite, and it's different than the next example. So anyway, we have discrete, which includes both of these cases. Finite is called discrete, but this one is also called discrete. Now we have another type called continuous random variable. By contrast, a continuous random variable takes on a continuum of values. Now what does that mean? For example, if x equals the number of gallons, or the number of liters, that pass hourly through a meter, with a meter means like some kind of some place where you measure the gas is going through. Anyway, it's just going through something, with a capacity of 50 gallons per hour. So the most that you can that can pass through this situation is 50 gallons per hour. Then its values could be any number between 0 and 50. Right? You could have in that 1 hour maybe 25 gallons or 25 liters went through, but it could be 17.2, or it could be 39.826. So when you have this many different possibilities, in other words, like every possible decimal number between 0 and 50, that's called a continuous, or it's called a continuum of values. And in that case, this x would be a continuous random variable. So if it's finite, or even if it's like this, then it's called discrete. But if it's like this situation, it's called continuous. That is, the random variable is called continuous. So what that means is, going back to here, if the set of values that x can take is discrete, so this is definitely discrete because it's just finite, then we call x a discrete random variable. So what determines it is the set of values over here that it can take. So if it's a finite set, it's certainly discrete. Even if it's a countably infinite set, it's still discrete. But if the set of values that x can take, that in this set here, is like a continuum of values, then we call x a continuous random variable. So it has to do with actually the range of the random variable. If the range is continuous, then the random variable is called continuous. If the range is discrete, then the random variable is called discrete. So he says, the mathematics required for continuous random variables is more advanced, requiring integration instead of just summation. Okay? So instead of just using sums, we have to use integral calculus. But anyway, that's the situation. We have two situations. One is called discrete random variable, and the other is called continuous random variable. Okay, let's look at some of these examples. In the planning of a 3-child family, assume boys and girls are equally likely on each birth. So here we're letting them be equally likely. That's not the realistic situation that he does apparently in his chapter 3, but okay. Find the probability distribution of x equals the number of girls. And okay, let's do that one first. So what would that be? Well, it should be fairly easy for you to do it. What are the values that x can take, first of all? So if x is the number of girls and you have 3 children, you can only have 0, 1, 2, or 3 girls. So that's the value that x can take, the values that x can take. That is, that's the range of the function, which is the random variable. And then figure out the probabilities for each of them. For example, what's the probability that x equals 0? Does that mean all boys? So what's the probability of 3 boys? That would be 1/2 times 1/2 times 1/2 in this scenario, where they're all equally likely. So that would be 1 over 125, right? And so on. So you should be able to do that. Okay, part B. Y equals the number of runs. Now, what does he mean by a run? A run is where a run is a run or string of children of the same gender. For example, y equals 2 for the outcome B, G, G, because we'd say first we had a string or a run of boys, even though it was only one boy, and then we had a run of girls, so we had 2 runs in this situation. Now, when you only have 3 elements in this list, it's a little hard to talk about runs, but if you had a lot of elements in the list, you could see runs. And actually, for example, this kind of thing might be interesting when you're talking about the stock market. So you might have a run of days when the price went up, and then a run of days where the price went down. And you might want to look at those runs. But anyway, he's just doing it for this for this example, as an example. So anyway, so you have to take each element in the sample space. These are the elements in the sample space. These are not the correct probabilities for his example, because he's assuming that in the problem that we're doing, he's assuming that boys and girls are equally likely, so you don't get these probabilities actually. But anyway, you have this sample space, and then how many runs are there here? 1. How many runs are there here? 2. How many runs are there here? 3. Right? B, then G, then B. So there's 3 runs. So you have to think about how many possible runs can you have when you have 3 children. So you can have you can't have 0 runs, right? But you could have just 1 run. Like if you had BBB, that would be 1 run, or GGG, that would be 1 run. So you have to think about how many runs can you have. You can't have 0. You can't have 1. Can you have 2? Yes. This is 2. Can you have 3? Yes, this is 3. Can you have 4? Of course not 4. So what did we say? You could have not 0, but you could have 1, 2, and 3. So the random variable that we'd be talking about would only have 1, 2, and 3 in it over here. And then you have to say which ones go to 1, which one goes to 2, which one goes to 3. And you do have to figure out this column first. That is, figure out the probabilities for each of these first, which I think, well, anyway, you have to do that. And then you draw the arrows to the right numbers over here, and then you have to figure out the probabilities for each of these. That's what he wants you to do, because he said find the probability distribution for this random variable, the number of runs. So that's what you're supposed to do. Okay, let's look at number 2. Actually, I'll stop this video and begin a new one.